Come to introduction to chemistry, an introductory and foundational course in chemistry for those people who seek to proceed with chemistry as a career or branches of chemistry like pharmacy, biochemistry, and biotechnology. So the prerequisite for this course, I urge all students to know by heart the first 20 elements of the periodic table, which are namely hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. I urge all my students to know these first 20 elements by heart and to be able to state the atomic numbers, the mass numbers, as well as the electronic configuration, including in the SPDF notation for the first 20 elements of the periodic table. That is a foundational aspect of chemistry, and it gives you a firm foundation to launch your career in as far as chemistry is concerned. Let us move on to the atoms and molecules. Firstly, the definition of matter. Matter is anything that has mass and occupies space or a volume. So basically, there are three types of matter, namely solids, liquids, gases. Right. So matter has got both chemical and physical properties. Remember, when we were in Form 1 and 2, we looked at chemical changes and physical changes, whereby we defined what a chemical change is, and we also defined what a physical change is. So that was foundational, and you are building on that to identify the chemical and the physical properties of matter. So this is a comparison of the physical properties and the chemical properties of matter. So basically, physical properties are characteristics of a substance that can be observed or measured without changing the identity of the substance. Whereas chemical properties are the ability of a substance to react to form new substances that can only be observed when it undergoes a chemical change that alters its chemical identity. So examples of physical properties include color, electrical conductivity, density, hardness, malleability, ductility, solubility, melting, and boiling points. We also have examples of chemical properties which are namely flammability, corrosion, neutralization, reactivity with water or acids, as well as chemical stability, toxicity, and heat of combustion. So this is elementary stuff which I expect you students to read and understand these things. Right. So basically, an element is a pure substance made of only one kind of an atom and cannot be broken down into simpler substances. For example, iron, represented by the symbols Fe. A pure compound is a substance of two or more elements which are chemically combined together in a fixed ratio. For example, water, which we knew even from as early as Form 1 that the chemical formula for water is H2O. A mixture is a combination of two or more substances physically mixed together in a variable ratio, where each component keeps its own properties. For example, air and salt water. So this is a comparison of elements, compounds, and mixtures in terms of the type of the substance, particle type, and separation methods. So basically, the elements are pure. They contain only one kind of an atom, and they cannot be broken down. Compounds, they are also pure. They contain fixed combination of different atoms, and they are separated only by chemical means. Mixtures, they are impure, that is variable composition. They consist of different atoms or compounds which are not chemically joined together. They can be separated by physical methods, for example, filtration, evaporation. That is the reason why salt water solution can be separated by vaporizing the water, and you'll be left with this solid salt on the ground after all the water is evaporated. We also look at solids, liquids, and gases. In terms of shape and volume, the particles, and the examples. So for solids, they have a fixed shape and a fixed volume. They are packed very tight in a neat fixed pattern, and they only shake or vibrate in place. Examples of solids include ice and bricks. Liquids, they have a fixed volume but no fixed shape. They take the shape of the container they are poured in. The particles are close together but not in a fixed pattern. They can slide and flow past each other. Examples are water and ethanol. Gases, they have no fixed shape and no fixed volume. They spread out to fill any container available. The particles are very far apart with a lot of space between them, and they zoom around quickly in all directions. Examples include nitrogen and oxygen. Right. We look now at metals, nonmetals, and semi-metals. Okay? For a good comparison of this, we look at our periodic table. But for now, let us look for the comparison under the following headings or properties: periodic table, appearance, state, conductivity, flexibility, and the respective examples. Metals. Basically, metals, they make up the majority of the periodic table. Metals, they make up the majority of the periodic table, and they are shiny and lustrous. They are mostly solid at room temperature, with the exception of mercury, which is a liquid. They are very good conductors of electricity and heat. In terms of flexibility, they are malleable, which means they can be hammered into sheets, and they are also ductile, which means they can be pulled into wires. Examples of metals, we've got iron, we've got gold, we've got copper, and aluminium. We also have what we call nonmetals. So nonmetals basically sit mostly on the upper right side of the periodic table. Their properties are mostly the opposite of metals. In terms of appearance, they are dull and not shiny. In terms of state, they can be solids, liquids, or gases at room temperature. In terms of conductivity, they are poor conductors of heat and electricity, and they are brittle as solids. They break or shatter easily instead of bending. Examples of the nonmetals, we have got oxygen, carbon, nitrogen, and chlorine. We also have what we call nonmetals. So these nonmetals, in terms of their position in the periodic table, they lie along the zigzag line that separates metals from nonmetals. They share a mix of the properties of metallic and non-metallic metals, right? They act as conductors. They share a mix of the metallic and non-metallic traits as well. Their electrical conductivity increases as they get water, which make them vital components for digital electronics and computers. They are brittle and non-ductile, and examples include silicon and germanium. So let us look at the periodic table to get an understanding of where our metals nonmetals, and metalloids are positioned. Right. So when we look at the left of the periodic table, that is where the bulk of our metals are, is represented by the pink color in the periodic table. Right. And the nonmetals represented by the blue color in the periodic table, they are mostly situated to the right of the periodic table, with the exception of hydrogen, which is situated close to where the metals are. And to differentiate or to form a demarcation between the metals and the nonmetals, we have got the metalloids, we have got boron, silicon, germanium, arsenic, antimony, and tellurium there. So that form a distinction of the metals and the nonmetals, and they are called metalloids, which are very, very important semiconductors with various applications in electronics as well as in computers. We now move on to solutions, suspensions, and colloids. So basically, a solution is a homogeneous one-phase system in which the solid particles, which we call the solute, are completely dissolved in the liquid substance, which we call the solvent. An example of a solution is a cetrimide solution, which is an antiseptic. Suspensions. These are heterogeneous mixtures or two-phase systems in which the solid particles are relatively large and they settle over time. The solid particles are called the dispersed phase, and they are completely dispersed in the continuous phase. For example, cotrimoxazole suspension. It is also important at this point in time to highlight that we have got two types of suspensions, which is the solid in liquid suspensions as well as the liquid in liquid suspensions. So the solid in liquid suspensions are called pure suspensions, and the liquid in liquid suspensions are called emulsions, which have got a very good application in the field of pharmacy. Colloids. Colloids are basically heterogeneous mixture in which the solid particles are intermediate in size, and they remain evenly distributed without settling. An example of a colloid is a fog, smoke, and gelatin. Let us now look at the comparison of the solutions, suspensions, and colloids under the properties. 1. Particle size, the type, stability, light, filtering, and examples of each. Solutions. In terms of particle size, they are very tiny, less than 1 nanometers. The type, solutions are homogeneous, which means they are uniform one-phase system. In terms of stability, they are stable and the particles do not settle out. Light can easily pass through solutions without scattering. In terms of filtration, the solutions cannot be separated by a filter. And common examples of solutions, we have got salt in water or sugar in water. Under colloids, the particle size of colloids is medium, that is from 1 to about 1,000 nanometers. They are basically heterogeneous in type, which means they are not uniform, even though they mimic a uniform mixture. In terms of stability, they are stable. Particles do not settle out on standing. In terms of light, they scatter a beam of light, a phenomenon called the Tyndall effect. In terms of filtration, they cannot be separated by a regular filter paper. And examples, like we have alluded to earlier, they include fog, milk, and gelatin. Now look at suspensions. They are larger, greater than 1,000 nanometers. In terms of type, they are heterogeneous, which means they are not uniform. They consist of distinct phases. In terms of stability, they are not stable, and heavy particles tend to settle down when left on standing. Light, they block or scatter light heavily, often cloudy or opaque. They can be easily separated by a filter. And examples include muddy water or sand mixed in water. They can easily be separated by a filter paper. Right. We now move on to protons, neutrons, and electrons. Right. So we are going to discuss this under the heading position in an atom, relative charge, relative mass, and behavior in an electromagnetic field. So when we look at protons, they are positioned in the nucleus. Their charge is positive and they have a relative atomic mass of 1 atomic mass unit. They are deflected in an electromagnetic field. When we look at neutrons, they are located in the nucleus of an atom. They are neutral. Their relative mass is 1 atomic mass unit, and they are not affected, neither they deflected in an electromagnetic field. When we look at electrons, they are located outside the nucleus in what we call electron shells. The relative charge is negative charge, and the relative mass is 1 over 1840, which is 0.0005 atomic mass units. So the electrons are deflected in an electromagnetic field. So let us now take this opportunity to have a diagrammatic illustration of the relative positions of protons, neutrons, and then electrons in an atom. So let us use an example. Let us use an example of sodium. Okay. So when we draw our sodium, for those of you who know sodium, they know that it's represented by a letter what? Na, sodium. Okay, right. So this is the atom. Okay, so this is the nucleus, and you are saying in this nucleus, that is where we have neutrons, and also we have what? Protons inside the nucleus. The neutrons, remember we said they are neutral, and the protons, they are positively charged, right? So sodium has got how many electrons in the outer shell? Okay, we know that the atomic number of sodium is 11, which means it has got 11 protons and 11 electrons. So that means in the outer shell, it has got 1 electron. So what are we saying? We are saying inside this nucleus of an atom, that is where we have got our neutrons and our protons. Okay? And electrons, they are not found inside the nucleus, but rather they are found surrounding the nucleus in what we call electron shells. Okay? So we now need to represent now our sodium in terms of its atomic number, mass number, right? So if we look in our periodic table, we see that the sodium is written as Na with 23 here and 11 there, right? And we know that in this notation, the 11, which is at the bottom, will be representing the number of protons, whereas the 23, which is on top here, will be representing the mass number. The mass number is also called the nucleon number, which is the sum of the protons and the neutrons. Okay, so what it means is for sodium, if it has got 11 protons, it means that the difference between the mass number and the atomic number is going to give us the number of neutrons. So the number of neutrons in sodium will be 23 minus 11, which is 12 neutrons. So this is the notation which we use when we are representing these elements in terms of their mass number and atomic numbers. So this is very clear. Let us continue with our PowerPoint presentation. Let us continue with our PowerPoint presentation. Right. So this is a diagrammatic representation of what I was illustrating on the whiteboard, whereby A represents your what? Your mass number, which we also called the nucleon number, which is the sum of the protons and neutrons of an atom. Z represents the atomic number, which is the number of protons in an atom. And X represents the symbol of an element. Remember, I said earlier on, it is very important and vital for all students to know by heart the first 20 elements in the periodic table, as it will help them in as far as determining the atomic numbers, the mass numbers, as well as the electronic configuration, which is a foundational concept in as far as the study of chemistry is concerned. Atomic number is the number of protons in the nucleus. The mass number, which is also called the nucleon number, is the number of protons plus the number of neutrons. We also have got another phenomenon which is very important in chemistry, isotopes. Isotopes are basically atoms of the same element with the same atomic number but different mass numbers due to a difference in the number of neutrons in their respective nuclei. Right. So nuclei is the plural of nucleus. When it is one, it's called a nucleus. When there are many, they become nuclei. So an example of isotopes, they are found in chlorine. Chlorine can exist as chlorine 35 or as chlorine 37. So kindly note, the number of protons will be the same, okay? Which is the atomic number will be the same, 17. What will be differing now to get a mass number of 35 chlorine and 37 chlorine will be the number of neutrons. So if atoms of the same element have got the same atomic number but different mass numbers due to the differences in the number of neutrons of the respective atoms, we call them isotopes. We now move on to orbital properties. Right. So let us pay particular attention to these orbitals. Right. We have got 4 types of orbitals, namely S, P, D, and F orbitals. Right. It's also very important at this point in time to know that these orbitals are represented by certain letters, right? The orbital type, we've got SPDF. They correspond to the first energy level represented by principal quantum number n, right? So basically, S orbitals, they are found in the first energy level, n is equal to 1. P orbital, second energy level, n is equal to 2. D orbital, third energy level, n is equal to 3. F orbital, fourth energy level, n is equal to 4. Right. We have got different shapes for these orbitals. Right? S orbitals, they are spherical in shape. P orbitals, they are dumbbell shaped. D orbitals, they are cloverleaf shaped. And F orbitals, they are complex or multi-lobed in shape. The number of orbitals per sublevel, spherical, they've got 1 orbital per sublevel, okay? The P, they've got 3 orbitals per sublevel. The D, 5 orbitals per sublevel. The F, 7 orbitals per sublevel. So each of these sublevels contain a maximum of 2 electrons. This therefore means for the S sublevel, it can have a maximum of 2 electrons. For the P sublevel, since they contain 2 electrons per sublevel, if it has got 3, it means that it will have 3 times 2, which is 6 electrons. For the d orbital, the number of orbitals per sublevel are 5, meaning that it will contain a maximum of 10 electrons. For the complex multi-lobed F orbital, it has got 7 orbitals per sublevel, meaning the maximum electrons per sublevel is going to be 14. So this is very, very important when we now move on to the electronic configuration of our atoms. Remember, I said it's very important for you students to understand or to be able to write the electronic configuration of the first 20 atoms, that is from hydrogen to calcium. We are continuing, right? So, S orbital, P orbital, D orbital, and F orbital. Basically, we've said the S orbitals, they are simple, round, spherical shape with the nucleus at the center. One orbital can hold up to 2 electrons. Okay? They are present in all main energy levels, starting from the first level, n is equal to 1. The P orbital is dumbbell shaped, 2 lobed on opposite sides of the nucleus, 3 orbitals holding up to 6 electrons. We have got 3 special orientations in the X, Y, and Z axis. They start appearing in the second energy level, which is n is equal to 2. The d orbital, they are cloverleaf shaped. 4 of the orbitals are cloverleaf shaped. However, the 5th has got an elongated dumbbell shape with a ring around its nucleus. It contains 5 orbitals, each holding a maximum of 10 electrons. It has got 5 distinct orientations determined by the magnetic quantum number ml from -2 to +2. They start appearing in the third energy level, which is n is equal to 3. For the F orbital, they are highly complex and multi-lobed, containing 7 orbitals holding a maximum of 14 electrons. The 7 distinct spatial orientations are determined by the magnetic quantum number m is equal to -3 up to +3, thereby giving us 7 distinct spatial orientations. They start appearing at the 4th energy level, which is n is equal to 4. Orbital properties. Energy level 1, we have got S sublevels. Available sublevels is 1s and 1s2. Okay, 1s and 1s2. Right. Energy level 2, sublevels is P. Available sublevels, we have got 2s and 2p. Right? And we know that the maximum number of electrons in an s orbital is 2. The maximum number of electrons in a p orbital is 6. Therefore, the electronic configuration will be 2s2 and 2p6. We move on to the third energy level, which is D, right? The sublevel is D. Available sublevels, we have got 3s, 3p, and 3d, right? We know that the maximum number of electrons in an s orbital are 2, in a p orbital there are 6, and in a d orbital there are 10. So the electronic configuration for energy level 3, we have 3s2, 3p6, and 3d10. The energy level 4, which has got sublevels F, right? We know the available sublevels in the 4th energy level, we have 4s, 4p, 4d, and 4f, right? Bearing in mind that the maximum number of electrons in S is 2, p is 6, d is 10, f is 14. It simply means that for the 4th energy level, we have got 4s2, 4p6, 4d10, and 4f14. We are continuing with our SPDF notation. So basically, an orbital is a regional space around the nucleus of an atom which can hold up to 2 electrons with opposite spins. A subshell is a single collection of orbitals of the same type. S subshell is a single s orbital which can hold up to 2 electrons. The shape is spherical, as we have alluded to earlier on. The energy, that is the lowest energy level among the orbitals. Capacity can hold up to 2 electrons. Example, the 1s orbital is the first orbital to be filled with electrons. We move on to the p subshell, a 3p orbital which can hold up to 6 electrons. The shape is dumbbell shaped, higher energy level than the s orbitals. Its capacity, it can hold up to 6 electrons, 2 in each of its 3p orbitals. Examples, the 2p orbitals are filled with electrons only after the 2s orbitals have been filled. We now move on to the d subshell, which is a 5d orbital which can hold a maximum of 10 electrons. The shape is complex. For example, cloverleaf. It has got a higher energy than the s and p orbitals. The capacity, it can hold up to 10 electrons, 2 in each of the 5d orbitals. The 3d orbitals are filled after the 4s orbitals have been filled. Right. We look at the f subshell, which is a 7-off orbital, which can hold 14 electrons. The shape, it is complex, which can be multi-lobed or diffused shape, octal or flower-like structure with 8 lobes or specialized cubes or general sets. It has got higher energy level than sp and d orbitals. Its capacity, it can hold up to 14 electrons, 2 in each of the 7 f orbitals. Example, the 4f orbitals are filled after the 6s orbital. Right. We are continuing with the electronic configuration in SPDF notation. So we've got certain rules to follow when we are doing electronic configuration in the SPDF notation. Firstly, we've got what we call the off-bow principle. The off-bow principle basically states that electrons fill the lowest energy levels first, meaning S levels are filled first before we can move on to P levels. Similarly, P levels are filled first before we can move on to D orbitals. And D orbitals are filled first before we can move on to F orbitals. We also have what we call the Pauli exclusion principle. The Pauli exclusion principle basically states that no 2 electrons in the same atom can have the same set of 4 quantum numbers. Then we have got what we call the Hans rule, which basically states that electrons fill degenerate orbitals, that is orbitals of the same energy, singly before pairing up. For instance, the electronic configuration of neon atomic number 10 is 1s2, 2s2, 2p6. This means neon has 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 6 electrons in the 2p orbitals. We are continuing with our electronic configuration. So, ladies and gentlemen, electrons fill orbitals in a way to minimize the energy of the atom. Therefore, the electrons in an atom fill the principal energy levels in order of increasing energy. The electrons are getting further from the nucleus. The order of levels filled looks like this, right? First energy level, 1s. Okay? If it is filled with 2 electrons, that's it. Second energy level, we have got the s and the p orbitals. So firstly, we fill the s and then we move on to the p orbitals. The third, we have got the 3s and the 3p and the 3d. However, kindly note that at the third energy level, we fill the 3s and the 3p, then we go to 4s. Why do we go to 4s? We go to 4s because 3d is at a higher level than the what? Than the 4s orbitals. After filling the 4s orbital, that is when we can go to 3d. Okay? So after 4s, we fill the 4p. After 4p, we then fill the 5s. Why so? Because a 4d orbital is at a higher energy than the what? Than the 5s orbital. And we continue like that. Okay? So, this diagram shows our orbital shapes. It is an illustration of our orbital shapes. But ladies and gentlemen, the objective of this lecture is for us to be able to do electronic configuration using the SPDF notation. So like I said earlier on, it is very, very important and vital for chemistry students to know by heart the first 20 elements of the periodic table. So for us to be able to have a study or a feel of the SPDF notation, we are going to list the first 20 elements of the periodic table, and then we are going to write their SPDF notation to try and see whether we have understood what we're doing, and also whether we have understood the Orbital principle, the Pauli's expulsion theory, as well as the Hans rule, because they are key in as far as the electronic configuration in SPDF is concerned. Also take note, this is the foundation upon which bonding and the properties of atoms in the periodic table, whether in the same group or across a period, vary. All this emanates from knowing the structure of these atoms, as well as knowing how their electron energy levels are filled in terms of the SPDF notation. So let us fill our first 20 elements. Let us fill our first 20 elements so that we get to understand the electronic configuration in SPDF notation. Right, so what did we say? We said the first one, it's with hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Right, so this is our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Right. So hydrogen, it has got an atomic number of 1. Therefore, it's going to be what? 1s1. Right. Helium, it has got an atomic number of what? 2, meaning it has got 2 electrons in the outer shell. It's going to be 1s2. Right. We have got lithium. Okay. We are now at the third energy level, so we expect to get what? 1 S2, okay, and 2 S1, okay. Remember, from the Orbital principle, it is the low energy levels which are filled first. Right, beryllium, we have got 1 S2, 2 S2. Okay, boron, 1 S2, 2 S2. Right, remember our S energy levels, they are filled by a maximum of how many electrons? 2 electrons. Then we move on to the 2p, in this case 2p1. Right, carbon, we have got 1 S2, 2 S2, and 2p2. Okay, nitrogen, 1 S2, 2 S2, 2p3. Oxygen, 1 S2, 2 S2, 2p4. Fluorine, 1 S2, 2 S2, 2p5. Right, neon, 1 S2, 2 S2, 2p6. Right, so let us check whether this is correct or not. Okay, we know that neon is a noble gas. All noble gases are stable, therefore all the orbitals should be filled. The s orbitals, they are all filled. The 1s is filled, the 2s is filled, the 2p orbital is also filled. Right, so we move on to sodium. Right, sodium, we have got 1 S2, 2 S2, 2p6. Then we move on to 3s1. Okay, magnesium, we have got 1 S2, 2 S2, 2p6, 3s2. Aluminium, 1 S2, 2 S2, 2p6, 3s2. Okay, then we move on to 3p1. Okay, then we move on to 3p1. Okay, then we have got silicon, 1 S2, 2 S2, 2p6, 3s2, 3p2. Right, phosphorus, 1 S2, 2 S2, 2p6, 3s2, 3p3. Sulfur, 1 S2, 2 S2, 2p6, 3s2, 3p4. Okay, chlorine, 1 S2, 2 S2, 2p6, 3s2, 3p5. Okay, argon, we have 1 S2, 2 S2, 2p6, 3s2, 3p6. Right, we should always check whether what you are doing is correct. We know that argon is a noble gas and is therefore stable. So at this stage, we need to look at whether all our orbitals are filled. The s orbitals are filled, p orbitals are filled, all the orbitals are filled. Therefore, it means so far, so good. Right, then we move on to potassium. 1 S2, 2 S2, 2p6, 3s2, 3p6. Okay, right. Here we don't write 3D. Why? Because 3D is a higher energy level than what? 4s. So we write 4s1. Okay, we move on to calcium. 1 S2, 2 S2, 2p6, 3s2, 3p6, 4s2. So that is the electronic configuration of the first 20 elements. Okay, as you can see now, for these p orbitals, okay, we were just writing them as numbers, s2, p6, okay, but we also need to draw the orbitals, the p orbitals, the 3 p orbitals, and then show the respective electrons in each of the orbital. Remember, we said it has got the p has got 3 orbitals, and the 3 orbitals, they are all filled with 2 electrons each, okay, but according to the principles which we have seen earlier on, the orbitals, they fill singly before they pair. So in the next lecture, we are going to be drawing all the s and all the p orbitals so that we get to understand. That will form the basis of our ability to be able to comment on the ionization energy across period 3, as well as the behavior across the various groups in the periodic table. So for today, I leave you to digest this stuff, and we hope to carry on in the next lecture. So thank you very much, and enjoy the rest of your day.